Hi guys, welcome back to my channel. So in this video we're solving this sample final exam using Green's theorem. Okay, so the question says find the closed integral using Green's theorem if the region is given by x equals to 1, y equals to 1, and it is between 0 and 1, and the portion of the circle. This is an equation of a circle centered at 0, 0, since it is not like x minus 1 squared and y plus 2, something like that. If it's something like that, that means we have an h and k, the center of the circle, but here there's none. That means the center is 0. Okay, so this is centered at 0, 0, and the radius is equals to 1. Okay, and it says that it's in the first quadrant. Okay, so let's go ahead and draw this region. So first we have x equals to 1. So x equals to 1 is nothing but simply a vertical line over 1. And then we have y equals to 1. So that is a horizontal line over 1. Okay, so this equation is y equals to 1. This is x equals to 1. And then we have the equation of a circle centered at 0, 0, and with a radius of 1. Okay, so let me draw a circle. This is centered at 0 and the radius. Okay, so it's gonna be a circle in the first quadrant, which means that you don't have to draw the whole circle like that. You only need it in the first quadrant. Okay, so you only need the circle inside the first quadrant. Okay, so this is how it's gonna look like. Only the region that belongs to the first quadrant. So then this means this is your region, right? This is the intersection of your region. So this is the one that you're going to use in order to find the Green's theorem. Okay, next. So I hope you guys remember the Green's theorem formula is really simple, that if you have something like pqx plus q dy, okay, so this is Green's theorem, which means the first expression that you have in terms of dx, this is the x component, so it's represented as p, and the second one is represented as q, which corresponds to the y component. Okay, so in order to solve it using Green's theorem, you just need to evaluate it, the corresponding region, and with qx minus py dA. Okay, so qx is nothing but simply you're going to take the q and integrate it with respect to x. Okay, so it's so it means the partial derivative of q with respect to x minus partial derivative of p with respect to y. Okay, so it is same thing as this. Okay, so let's go ahead and solve it. So we have first q of x, so this is q and partial derivative of q with respect to x. Okay, q with x, that means y is a constant, so it goes to 0, so you're only differentiating x, so you have 2x. Now what about py? So this is p, and p with y means x is a constant, so that goes to 0, and you only differentiate the y part, so you have negative 2x to y. Okay, now let's go ahead and plug this into the formula. So you have qx minus py, so this in the formula there is already a minus over here. Okay, in your formula there is already a minus, but there's a minus over here as well, so then this is gonna turn out to be 2x plus 2y dA, and of course the region that we need to figure out over here. The bounds, the limits, we're going to find it using this region. Okay, so if you think about it, here you have circles involved. Okay, so that means you need to use the polar coordinates, right? But if you use polar coordinates, you need to convert it into polar first, of course the region, but then you need to find the r. Remember, we need to find r equals to, and then we need to find the angle, angle as well, right? The angle and the r. Okay, but here to find the r, we always had the radius equals to 0, right? I mean the radius centered at 0. Okay, so if this was our region, only this, then we would use polar. It would be really easier for us, because here we have radius from 0 to, we have r from 0 to r equals to 1, since we are inside the circle, right? But here this is not our region, right? This is not our region. Our region is this right over here. Okay, so here we don't know the radius of this region because this is not a circle, right? So that's why we cannot use polar. But if we use the rectangle region, this is gonna be really hard for us, because it involves square root and something, right? Because we need to solve for x and we need to solve for y, so that's gonna be like square root x equals to square root of x squared plus 1 square root, and then it's gonna involve a lot of integrals, and it's gonna make it really hard for us. So our simple way here is to split this question into two parts, region 1 and region 2. Okay, so our first region, it's gonna be the rectangular region that you see over here. Okay, so this is gonna be our region 1, and then you're going to take the integral, the area of this region that you see over here, the rectangular region. Okay, and then you're going to subtract it from this circular region that you see over here. Okay, so if you subtract that rectangular region from this region, so this is what it's gonna give you, right? So it's really simple. Okay, so if you don't understand, so let me explain again. Okay, so you have this triangle, this square region over here, right? So you're going to take this and then you're going to subtract the circular radius that you see. Okay, you're going to subtract this from this, and which is eventually gonna give you the region that you are looking for. So you're looking for this region, right? Yeah, so you're looking for this region right over here. So you just need to subtract this from it, so which is gonna give you this. Alright, so let's go ahead and do this. Alright, so let's go ahead and name these regions. So this is region 1, this is region 2, and this is the actual region that we're trying to find. Okay, so to evaluate the region 1, we're going to take this integral 2x plus 2y, and the limits of integration, we're going to use this region. Okay, so first we can of course choose to go in the dx direction or in the dy direction. So let's choose to go in the dy direction first. That means we're going to write dy dx, right? And here we need to find the bounds from the graph. Okay, so first of all we need y equals to equations. Okay, so which means, okay, remember in the Green's theorems video I told you guys, if you wish to go in the dy direction first, then you go inside the graph, you go in this direction. Okay, but if you wish to go in the dx direction first, which means you go in this direction. Okay, from left to right in the dx direction, from bottom to top if you wish to go in the dy direction. Okay, so remember our region now. So don't forget, this thing is our region. Okay, for now, this is not our region for now. our region is hold this for right now. Okay, we're taking the region 1. We're integrating, remember, the region 1. Okay, so this means we need to go inside this region in the dy direction. So this is how we're gonna go, right? So here we need to know the equation of this line and the equation of this line in terms of y. So the equation of this line in terms of y is nothing but y equals to 0. And what about the equation of this line? So we already know the equation of this line is y equals to 1. Okay, so I hope you guys understood. So if you're not, let me explain again. This is our region. We go in the y direction. We find the equation of this line and with this line, which is 0 and 1. Okay, so the equation of this line is y equals to 0 to y equals to 1. And what about the x? For the last variable, you only look at the constant. You don't look at the equations. Okay, so where does this region belongs to in terms of x? So this region belongs to in terms of x. So the lowest one, x value here is 0, and the highest x value is 1. Okay, inside the rectangular region. So x values goes from 0 and 1 as well. So now, once we have our limits of integration, we can finally go ahead and solve this problem. So first we are integrating it with respect to dy. Okay, so this is a constant, x is a constant over here. We're simply going to put a y in front of it, and here, since it's a 1, so that's going to be to the power of 2 over 2. So these 2 and 2 is going to cancel out, and we need to evaluate it from y equals to 2, 1 to y equals to 0, sorry. Okay, and yeah, not forgetting the integral. Okay, so now these 2 it cancels out. So evaluated by plugging in 1 inside this equation, so you get 2x plus 1. Okay, and then minus 0, because this is going to give you 0 and 0, so you don't need to write a 0. Okay, so now we can finally go ahead and evaluate it from x equals to 0 to 1 in terms of dx. So this is 2x squared over 2 plus, since it's a constant, we're going to put an x only. Okay, evaluated from x equals to 1 to x equals to 0. So now let's go ahead and plug 1 inside it. This becomes 1 plus 1, and of course a 0, that's going to give you a 0 only. So you get 2 as a final answer for region 1. Okay, so you got 2 for this one. Okay, okay, so you got 2 here. So let's go ahead and find what do we get for this one. Okay, now we are evaluating. Now we are evaluating the same thing, but for region 2 this time. So we have our qx minus py dA for region 2 this time. Right? Here we're doing the exact same thing, 2x plus py dA, but with the region 2 now, and region 2 is being circular now. Remember this circular region? And every time we have circles involved, what do? Correct, we switch to polar. Okay, so for polar, remember guys, it is r is always equals to r cosine theta, x is always equals to r cosine theta, and y is always equals to r sine theta. Okay, so let's replace these values with the given values. Okay, so we have r cosine theta plus 2, and y replaces with r sine theta dA. Okay, so now let's go ahead and replace these with the corresponding r and the angle. So what is the r that we have over here? So here this is our region 2, and the r that we have here, this is from r equals to 0 to, what is the radius of this circle? This is 1, right? So it's r equals to 0 to r equals to 1. Okay, so the r goes from 0 to 1. And what about the angle? So the angle, since it only belongs to the first quadrant, so here we start at 0 and we finish at the first quadrant 90 degrees, which is pi over 2. So pi over 2, 0 to pi over 2. And yeah, by the way, 2 are, if you just remove the brackets, because you just need to multiply it, right? So no need to put brackets. Okay, so you have 2r cosine theta, and here remember we have r first. Okay, so it has to be dr d theta, right? Because we have r first, so that means we have dr first and d theta. And for the polar coordinates, this is very important. You need to multiply the expression within r. Okay, this is very important. It is always r dr d theta. Don't forget this r. This is very important. Okay, r dr d theta. Okay, so now let's go ahead and multiply with this r. So we have r squared cosine theta plus 2r squared sine theta dr d theta from r equals to 1 to r equals to 0 to 1. And theta equals to 0 to theta equals to pi over 2. So next, let's solve it in terms of the r first. Okay, so we're only differentiating the r. So integrating the r to the power of 3 over 3 cosine squared plus 2r cubed over cube sine theta, differentiate from 0 to 1. Sorry, from 1 to 0. Messed up. And at the end we have the thetas, of course. Okay, now plug in 1 and 0 inside the r. So here we're left with 2 over 3 cosine theta plus 2 over 3 sine theta, and if you plug in 0 inside the r, you're gonna get 0 and 0 inside this expression. Okay, so you don't need to write it. Okay, now let's move on to theta finally. So finally we can go ahead and solve this. So if you remember, the derivative of sine is cosine, and the derivative of cosine is the negative sign. So the integral is nothing but the inverse of derivative. Okay, so here we already have sine, and we want to go into cosine. Okay, so here I'm talking about this one. Okay, so if we have sine, we want to go to we want to inverse the sign. So what is the if we undo the derivative, we get cosine, right? So here we get 2 over 3 cosine, but a negative because it has to be a negative sign. Okay, here we have cosine in the derivative because integral is used to undo the derivative, right? So we're simply undoing the derivative. So here we have cosine, or what do we do if we undo the derivative? We get sine. Okay, so we get sine if we undo the derivative. And we have negative over here, right? Now we have theta from 0 to theta pi over 2. So let's go ahead and plug in pi over 2 first. Sine of pi over 2 minus 2 over 3 cosine of pi over 2 minus 2 over 3. You're going to plug in 0 inside, and minus 2 over 3 cosine of 0. Okay, so what do you get if you do that? Okay, so this is gonna give you a 1, this is gonna give you a 0, and then this is gonna give you a 0, and this is gonna give you a 1. Okay, so if you multiply this, so this is 2 over 3 minus 0 of course, okay, and then this is gonna be, if you multiply this negative inside, so that's gonna be positive 2 over 3. Okay, so you have positive 2 over 3. So then it becomes 4 over 3 for the region 2 of course. Okay, so we get 4 over 3. 4 over 3 for the region, but we want to find for the original region, remember here. So here, in order to find the final answer, we simply need to do, let's take this integral, right, 2x plus 2y dA, and we're going to write this is equals to 2, this is equals to region 1 minus region 2, and we know the region 1 is equals to 2 and the region 2 is equals to 4 over 3. So the final answer turns out to be 2 over 3. And this is your final answer. Thanks for watching. Bye.